As we finish this unit on exponential properties with lesson 6.2b, we're really going to just bring together two topics that we've already covered. So there's really not any new content in this particular lesson and notes. It's really just bringing together some of the properties and the rational exponents that we had already discussed in previous lessons. So the idea is we're going to take those rational exponents, which again, it just means really exponents that can be fractions. And we're going to apply the product and the quotient properties, but just working with the fractional exponent. So we're still going to be talking about like, oh, when you have like bases and you're multiplying, I know I can add those exponents. Or when we're dividing and we have like bases, we can subtract those exponents. The big difference is that now we're dealing with exponents that are not just whole numbers, but they might be fractions as well. So we're just bringing those two lessons together. So let's get started. And you have a few pointers here just to remember, hey, when you do things like this, you might have to dig back to some basic skills like the fact that you need common denominators when you add or subtract. Okay, you combine those fractions as necessary. Make sure that your answer is simplified. So if you get something like 2 over 4, simplify that kind of thing. And then at the end, make sure that you've cleared any negative exponents. So let's do a few practice problems here, starting with number 1. So the first thing I want to notice is they have like bases. So I can use my properties in this problem because the two bases are the same. So I've got a base 3 power right here and a base 3 there. And then the other thing I want to recognize is that this is a multiplication problem. So that means I can use the product properties that we learned last week. So when we do that, when it's multiplying two like base powers, we know that we can combine those fractions. So I can write this as a single power by taking that negative 2/3 exponent and adding the 7/3 to that. So that's the big idea there. And then if we didn't already have it, then our other option or our other focus would be to make sure that we have like terms before we proceed. But we got lucky with this one. It does have like terms, so we can go ahead and perform that fraction operation. I know that a -2 and a +7 is just a +5. So those fractions combine to a 5/3. And then as long as this fraction is simplified and it's positive, if I see the math is easy enough, then I can go for it. But if not, then this is my answer. I'm looking at this, and I know this really means taking the cube root of 3 and then raising that to the second power. But I know the cube root of 3 is nothing that I want to deal with right now. It's a terrible decimal. It's one of those irrational decimals. I would need to grab the calculator. We're not going to bother with that. We can definitely leave our answer as a power if it doesn't come out, easily and, nicely, a whole number. And we'll just leave it like that, just making sure that those prerequisites here are met, that it's positive, it's simplified, and we've done as much math as we can do here without going to the calculator and getting a gross decimal. So there you go. Let's try number 2. This particular problem still has those like bases. So we've got a base 7 and a base 7, but it's division. So I want to use the quotient properties for this one. The quotient properties say that when you have like base powers and they're being divided, I can subtract the exponents. So I can write these guys together as single power by taking the first exponent and then subtracting the second one. Well, that's minus a -5/4, and we know when we have a double negative, that really becomes a positive. So we end up with 7 3/4, 7 to the 3/4 plus 5/4. That's the operation that we're going to do with the power, with the exponents up here. And then I have like denominators already, so that's good. So 3 plus 5 is 8. So we get 7 raised to the 8/4. Now in this this is a really great example of something that we can simplify. So I want you to be able to see this 8/4 and acknowledge, oh yeah, that simplifies. I know that 8/4 is just 2, right? So all of a sudden that got real, it started off kind of pretty ugly looking, but it ended up just being absolutely equivalent to 7 to the second power. And so you can leave it like this, or in fact, since we know what that is easily off the top of our head, we can even write it as 49. And this is really the best answer right here, that our answer is 7 squared and that is 49. Okay. Let's try the same here. So like bases, check. multiplication, sounds good. That means we'll use the product property. The product property tells us that we'll be able to write this as a single power and just take those fractions and add them together. Okay, and this is kind of where our luck runs out a little bit as far as denominators. So we know that we can add those, and we can use a property, but we don't have like terms here. Like common denominators there. So we're going to have to accomplish that. So the easiest common denominator between 3 and 6 is 6. So that means I can leave this alone, and all I would have to do is double this and multiply times 2 on the top and bottom there, so that it really becomes 4 over 6, okay, plus the 5 over 6. So all I had to do was double this fraction, and I get the common denominator that I need. And now I can go ahead and do that. So when we do this, 4 plus 5 is 9. So we get 9 over 6 in our denominator. And 9 over 6 simplifies, so let's do that. That means that we're taking this negative 1/9, not negative, this just 1/9, and we're raising it really to the 3 over 2 exponent. And I probably would take this answer like this, but I would love for y'all to see this and know that you can actually keep going pretty easily here, because we have those quotient properties that we can distribute that exponent, so we can really apply this exponent to our numerator and our denominator. And then from the previous lesson, we learned that when there's a denominator, it's really that root. So what they're asking for here is the square root of 1 raised to the 3rd power and the square root of 9 raised to the 3rd power, both of which I think are pretty doable. So if we do the square root of 1 is 1, because 1 times 1 times 1 3 times is 1. So that's sorry, this is a square root. So yeah, it's still 1. It's just 1 times 1 is 1. So the square root is still 1. And then the square root of 9 is 3. And then these are still being cubed. Okay, because square root of 9 is 3, because 3 times 3 is 9. And then we can then cube that. Well, now that's when we do it. So 1 times 1 times 1 is still 1. There it is. And then 3 times 2 times 3 is 27. So our final answer for this one, if we really wanted to just go all out, would be 1 over 27. With that said, if you got to here, at this point right now, you would get credit. But little by little, I want us to be able to get all the way to that final answer, if it works out nicely. If it's going to be like this guy where I know I will get a decimal, don't bother with that. But if you can get it nicely here, if the math is simple enough, then go for it. Okay, so at this point, I want y'all to pause the video. I want y'all to try all 3 of these on your own, and then in just a moment, you can check your work and see how you did. Okay, so check your work on these. These are all kind of pretty close to being done or done. So for the division, did you subtract the exponents, get a common denominator, and get a 3/4 for number 4 here as your resulting power? Check that. If you did, then really that's all we can do, right? So once I'm here, I don't know what K is, so I can't actually evaluate this. And this is already simplified and positive. So for this one, this would be our final answer, and as far as we could go. For this one, same thing, division. So we're subtracting those exponents. I did need to get a common denominator, so I went for 4 over 2 here, so we would have that matching denominator, and then I could find the difference, and it's 1/2. However, we talked about this yesterday. Exponent of 1/2 really means take the square root of 64, and that we can do. We should hopefully know that off the top of our heads, that the square root of 64 is just 8. So that one we can clean up all the way to a final answer. And then number 6, it's multiplication. So I'd be adding those fractions. I will need a common denominator there, so I went for the 12, the smallest one. And then that allows us to combine those. When we combine a negative 14 and a positive 3, though, we get a negative 11. And one of our, big criteria is making sure we only leave positive exponents. So the final step, and really the only thing I can do that's left, is write this as its reciprocal. And then that's as far as I can go without knowing what m is. We're done. but it does need to be positive. So if you need to finish out that last step, that's what you would do. Okay, so now let's look at 7 and 8 here. And on these guys, these are a little bit more complex, so hang in here with me and follow along. There's more than one thing, and that's where you have to just be careful is with these coefficients. So in this first one, it's this quantity right here being divided by that. And if it helps, I might actually recommend that it might be better to just at least quickly reorganize this in that vertical division, so that you can see what's going on here. Okay. Oh, and this is a negative. So that's a negative 1/9 up there, at least for now. So if these are both saying the same thing, let's just write it vertically. But what I'm getting at here is I want to just remind you of a couple things. That 3 is part of your divisor, what's being divided, your dividend, what's being divided. So it should be on the top. And it's also not part of this exponential, right? So this power up here, this negative 1/9, it's only on the p. Okay, so if that helps, if it helps to write it this way, go for it. And then I realized, well, the 3 is just going to be there. There's nothing that I can simplify it with, combine it. It doesn't have a negative exponent. It's still going to be where it is. What I really need to work out is what is happening with these p values. So that 3 is going to stay up here. And then let's figure out what's going to happen here. Since I'm dividing, I would subtract that negative 1/9 exponent minus this negative. Except minus a negative is really just plus that 2/3. Okay, so the 3 is going to stay up there, and then I'm going to compute this by just doing this power minus that power, which gives me that. And then I want to realize, oh, but wait, we don't have a common denominator here. I need a common denominator of 9, so maybe I'll rewrite this multiplied by 3 and rewrite that 2/3 as 6/9. Now I have a common denominator, and I can combine that negative 1 and that positive 6, and that leaves me with p to the 5/9. Okay, since it's positive, it could stay in the numerator at the top. I don't have to bring it down. This is our final answer. Just like that. Okay, so the 3 stayed in the numerator the whole time, or as part of what was being divided, and then our exponent ended up just being a positive 5/9, so that stays at the top as well. And then in number 8, be real careful with this one, because that 7 is part of your divisor, is what you're dividing by. So it might be easier to see in the vertical method again, but that's in your denominator. You're dividing v to the 1/3 by that 7v to the 3/2. So that's really what's happening, and I just want to exemplify that because I want you to notice that if you're dividing by 7, that 7 needs to be in the denominator this time, and it's not part of this, so it's going to stay in the denominator even when it's all said and done. So now for the exponents, we'll do the subtraction like we did before, since this is division. So to work out what's going to happen here, we're going to do kind of off to the side. What if we do that 1/3 minus the 3/2? So top exponent minus the bottom one. And I need a common denominator for those guys. So I'm going to make that a 6. That makes the 1/3 be a 2/6. And for this one, it would be 9/6 there. And now I can actually work out what the power is going to be. 2 minus 9 is a negative 7/6. So the fact that that comes out negative is just an indicator to me that I'm going to have to put that in the denominator with my 7 to clear the negative exponent. So coming back here, when I kind of take care of these guys, this is going to end up in the denominator. So it's going to be 7 down here, and then a v to the positive 7/6. That way I can write it as a positive exponent. And that would be our answer. Okay, so that's the main thing. It's just make sure that if you have whole numbers involved and these kinds of things, that they end up in the right place here. So it's 1/, and everything really ended up in the denominator for that one. All right, so that is just kind of our practice. We're nothing new here. We know how to add and subtract fractions. We've done that since we were little in elementary school. And then we've talked about these product and quotient properties, and we've talked about the rational exponents, and we're just bringing it all together. Okay, so let's finish off with a few word problems. On well, I guess we should have numbered that number 9, but we'll be all right. So number 7, we've actually done this problem before, so I'm going to actually, well, I'll set it up and we can do it quickly. But we've done this one either with similar numbers or the same numbers in the past. They tell us here that the radius of a sphere can be given by this formula. You're going to put the area over 4 times pi, and whatever that quotient is, you're raising to the 1/2, which really means just the square root, I mean. And in this particular example, the surface area of our sphere is 2,122, so that's what I'll insert here, 2,122.64 over, and then they want us to use the 3.14 for pi. So we just insert what we know into the problem so that we can find the radius. So they gave us the formula. They tell us the surface area is 2,122.64. Find the radius to the nearest tenth using 3.14 for pi. So this is the formula that will give me that. I insert what I know, and then if we simplify this, parentheses first, we've talked about that a few times. It would be foolish of me to try to get that, the square root of all of these things where I could just clean the inside first and then only have to take 1 square root, right? So I'm going to work on this interior part. When I do 4 times that pi, I get 12.56. And then honestly, this really pays off, because if and when you grab the calculator and you do that 2,122.64 divided by this, you get a perfect 169. And so that's a great example of why it's nice to just simplify inside first and then work with that exponent. So parentheses first, right? Because it turns out, if you weren't quite already sure, that 169 is a perfect square. If I take the square root of 169, I get exactly 13. So that sphere would have a radius of exactly 13 meters. Yeah. So these, they look long, but really most of it is just about kind of inserting numbers in the right places in the formula and then just simplifying, practicing how to simplify. And some of them we may need to reach the calculator. This was not one of those. Let's take a look at the next one. This one is new. It is a little bit different, and it has a little typo. So join me here as we insert the missing h into this formula, which should be right there where that gap is. The problem. So it says, on a roller coaster, your speed in a loop depends on the height of the hill that you just came off of, as well as the radius of the loop in feet. And then they give you the equation where the velocity is equal to 8 times h minus 2r raised to the 1/2 power. That'll calculate the velocity of the car at the top of the loop. So that's like right here. Suppose that your loop has a radius of a radius of 18 feet. So they just gave us the r that we're going to insert there. And then if the hill is 50 feet, boom, they just gave us a height, what would the velocity be? Okay, and we're going to round to the nearest 10th place, so keep that in mind. So let's look at our formula. You got volume equals, velocity equals, so used to that, 8 times h minus 2r to the 1/2. And now let's insert what we know. So we want to calculate this velocity. If the height of the hill that we just came off of is 50 feet and the radius of the loop is 18. So that's where we're at. All right, now let's clean this up. So same thing. There's no point in me distributing all this when I could just clean up what's inside that parentheses first. So multiplication before subtraction, of course. 2 times 18 is 36. This is all, this is really all about order of operations, guys. So even within the parentheses, multiplication before subtraction, we know that, right? So we get 36. And then we calculate what 50 minus 36 is. And that happens to be 14. Okay, and it isn't until we're here that we really need to consider this exponent. Now that all the math in the parentheses is done, we do know that we do exponents before multiplication. So we're not going to do these guys together. We're going to take that square root first. That's 1/2 really means take the square root. And this is where I think we can all agree, well, 14 is not a perfect square, and we're going to have to reach for our calculator here, which needs to be charged apparently. But let's go ahead and take the square root. You can either do the radical version of this and take the square root of 14 this way, or you could just raise 14 to the 1/2 power. They should both give you the same answer, right? Either way, this decimal is approximately 3.74. I'm going to just round it there for now, but I'm going to use the exact one on my calculator. Y'all know how I like precision. And then once I've taken the exponent, then the last step is to multiply that by 8. And when we do that, this velocity is approximately, since we're rounding, 29.9, since we're rounding to the nearest tenth. So we're looking at 29.9 feet per second, right? So 29 point, oh, that's not a 9. 29.9, and this should be velocity in feet per second. Yep, that's our units here per second. Okay, so there it is. That would be the velocity of the card at the top of the loop. Okay, let's try one more. This one is a lot like actually the first one up here. So actually, if you want to pause and try this one on your own, that's probably a good one to do that for. Press pause, try it out, and then you can fill it in. Okay. And this radius equation, this is for a sphere still, but this is has to do more, instead of the surface area, it has to do with the volume. So this formula gives us the radius, where V is the volume of the sphere. We're still dividing by 4 pi, and that is all now going to be to the 1/3, or in other words, we're taking the cube root. And it asks us to find the radius of a basketball if that basketball has, right here, 463 cubic inches in volume. So they're giving us the volume, it's just over here, and make a note of that. But that's going to be the V value, and they still want us to use that 3.14 for pi. So let's go ahead and fill in what we know. Here at the top is going to be 3 times that 463. That's the volume. And on the bottom, it's going to be 4 times that 3.14 they want us to use. And we're going to calculate all that, and then we're going to take the cube root of it. And they want us to calculate this to the nearest inch. So let's go ahead and simplify some of this. So when we do 3 times 463, I get 1,389. 389. And that's over, and we already know that 4 times pi, we did that earlier, is 12.56. And I'm still going to divide that before I even deal with that exponent, right? Parentheses first. So when I do this, divided by that 12.56, looks like we get about 110.589. So this is about 110.589 approximately. And then we want to take the cube root of that, and that's going to tell us what this radius of this basketball is. So I can go to math, pick that fourth choice. Oh yeah, I can see that. The fourth choice there is the cube root. And then I can come up here and just grab this, or you can recopy it. But when it's all said and done, we're looking at a radius of about 4.7999999 and so forth, right? But it does say to the nearest inch. So actually, we're just going to round to the nearest whole number here. So when it's all said and done, the radius of our basketball is approximately 5 inches. If we round that to the nearest whole inch. There it is. So most of these are really about just plugging it into the formula and then just making sure you're doing that order of operations and that you understand what that exponent really means. It's taking the cube root or the square root and so forth. All right, and then tomorrow we'll practice these more, and then this wraps up our whole lesson over exponential properties.